Swayam Prabha. Digital India. Educated India.
Hello everyone, this is lecture 2 of module 3. In module 3 we started with the basics of the surface waves. In the previous lecture we discussed about the basics of surface waves such as what are Rayleigh waves, what are love waves, and we have seen the particle motion of Rayleigh and the love waves. Now in this lecture today we are going to do the derivation of the Rayleigh wave, and then we will also be talking about the particle motions of the Rayleigh wave. After that we will be having the summarized lecture of today, whatever we will be covering. So regarding the Rayleigh waves are basically a combination of trapped or the evanescent P and SV waves that exist at the top of the half space. So since we are talking about the surface waves, so at the surface the tractions must be 0. So the traction, that is why it is written where there is a zero traction surface condition. So since we are deriving the equation for the Rayleigh wave or its displacement, we want to see how the displacement in x direction and z direction behaves and how the combination of those two displacement along x and z gives rise to the particles retrograde and the prograde elliptical motion in the Rayleigh waves. For that purpose we are going to do this derivation, and let's consider the P and SV wave are the wave equation in the terms of the potential we are considering. So for the P wave we are defining this term phi, and there is for the SV wave, as we have seen in the previous lectures, we are defining this term psi, and the phi is basically having the equation a e to the power minus iota in bracket omega t minus kx r alpha z. For the SV wave, psi is equal to b e to the power minus iota omega t minus kx x minus kx r beta z. So kx is the horizontal wave number, and x and z are the positions, and then we have this term r alpha and r beta. And we have seen in the previous lecture that the r alpha is basically equal to the vertical wave number divided by horizontal wave number, or you can say it is the ratio of vertical to the horizontal wave number. And if suppose the cx is the apparent horizontal velocity of the wave, then we can write this thing as cx neta alpha, where neta is the vertical component of the slowness. So if we write this neta alpha from the equation, if you remember that the p square plus neta square is equal to 1 by alpha square. So if we remember that, then we can write neta as equal to 1 by alpha square minus p square to the power under root. So that is what it is written here, and then we can basically take this cx into this bracket, and then it will become cx square by alpha square minus cx square p square to the power 1 by 2. So this cx into p will basically be equal to 1 because p is equal to 1 by cx. So that is what it is written here. So r alpha will now become cx square by alpha square minus 1 to the power 1 by 2. Likewise, you can see what r beta is. R beta will become cx square by beta square minus 1 to the power 1 by 2. And this r beta, in r beta what we have basically done, we have just replaced alpha by beta here. So for the energy to be trapped near to the surface, the exponential term, so these exponential terms here, must have the negative real exponent. So what will happen in that case? If this will be having negative real exponent, then what you need to do, you need to basically consider this particular situation that we did in the previous lecture for the evanescent wave. So Cx should be less than beta, should be less than alpha, because in that case only this will become less than 1, and then this entire thing will become imaginary. And when you have this imaginary term, then when you will multiply with the iota here, then it will become the real exponent. So now if you do that, then what you can do, you can take -1 out of this bracket. If you take this -1 out of this bracket, then out of the bracket you will get negative iota in bracket 1 minus Cx square by alpha square to the power 1 by 2, and then r beta will become something like this. Now we know that for the surface wave, the one condition that should hold true at the free surface is the shear traction must be 0, and then for the shear traction must be 0 at the surface, this sigma xz should be equal to sigma zz, that will be equal to 0. And if you want to calculate these components of the stress tensors, then you can basically use this form of the Hooke's law, which is in the form of Lami's constant, and where theta is the dilatation term and the delta ij is the Kronecker delta function. This is the Kronecker delta function, and this lambda is the Lami's parameter, mu is the shear modulus, and this Eij is the strain tensor. So now relate the stress to basically to the deformation. If you remember, we can write the stress terms in terms of the displacement. In terms of the strain, then you can see, if you will define that the z is equal to 0 into this particular equation, then it will become sigma xz x comma 0 comma t, that will be equal to 0 from this boundary condition, and that will be your 2 mu exz, and exz can be written in this particular form, and that is basically mu in bracket del ux by del z plus del uz by del x, and sigma zz x comma 0 comma t will be lambda theta plus 2 mu ezz, that will be equal to lambda in bracket the dilatation term theta, that is del ux by del x plus del uy by del y plus del uz by del z, and this term can be written something like this. So 2 mu del uz by del z. So in order to solve for the displacement, you can write the displacement in terms of the potential using these particular equations. So ux will be something like this, and the uz will be like this. So phi is the p wave potential, and the psi is the s wave potential. Now in order to solve for this, you can usually take the derivative del phi by del x, del psi by del z, del phi by del z, and del psi by del x from the equation that is written over here, and then you can incorporate into the equation for the stress, and then what you will get the sigma xz for at z is equal to 0, that is equal to 0, 2 mu exz, that we have already seen just a while ago, and that will basically become this thing, because you can basically solve this for the phi term, that is you can write the u in the terms of the potential for the p wave and s wave, something like this, and for sigma zz at z is equal to 0, that will be your lambda theta plus 2 mu ezz, that theta is the dilatation term, and this thing can be written something like this, and in terms of the potentials, this will become something like this. Now you can add these into these equations, okay, and then find out the values of this, and this, and this, likewise for this as well. Likewise you can take the respective derivatives to get these values. Now we are not going into the details of doing those derivations, but you can, if you will solve those, then you will get these two equations. So this is sigma xz x comma 0 comma t, that will be equal to 0, that is equal to 2r alpha a, that will be equal to 1 minus r beta square beta. Beta is the shear wave velocity, sigma z x comma 0 comma t, that is 0, the direction should be 0. So that will give you this particular equation in the form of r alpha and r beta. So we know that 1 plus r alpha square is equal to cx square by alpha square, and we also know that rho alpha square is equal to lambda plus 2 mu, and then we also know from the shear wave velocity formula in terms of the shear modulus is equal to this, mu is equal to rho beta square, and we can substitute that, all these three things we can substitute that into these two equations to get these two equations. Okay, so when you get these two equations, now these two equations, what it tells you, there are two unknown parameters, and you now have two equations, a and b are the two unknowns, and these two are the equations. This is your equation 1 and that may be your equation 2. So when to have the non-trivial solution, the one thing that must be happening is the determinant should be 0. In order to have the non-trivial solution of this system of equation, you need to have your determinant should be equated to 0. So when you do so, the resulting equation that you will get will be like this, and this particular equation is basically known as Rayleigh function. Remember that this particular equation is known as Rayleigh function, and this Rayleigh function can also be written in the another form, something like this, in terms of p and alpha and beta. It can be written something like this. So in Stein and Weissation book, you will find the Rayleigh function something like this, and in the book of Shearer, it is written in the form something like this. So to simplify this, you can assume the Earth to be a Poisson solid. At least for the case of upper mantle, this is a very good approximation that the Earth is a Poisson solid, and its nu is 0.25, and the ratio of the square of the p wave velocity to the s wave velocity should be equal to 1, or you can say alpha by beta is equal to under root of 3. So when you will incorporate that into your Rayleigh function, then what you will get your equation in the form of horizontal apparent velocity, that is your cx, and in the form of beta. So you can see this is the final equation that you will get in the form of cx square. So you can see it is a cubic in the form of cx square. When you will take the root of this equation, the only one root of this equation will satisfy your criteria, and your criteria was cx should be less than beta and beta should be less than your alpha. If you remember, in the previous slide we said that the wave should be trapped near to the surface. In order to do so, the exponential in the z must have negative real exponent. So in that case, this particular function r alpha and r beta should be imaginary. In order to have imaginary values of r alpha and r beta, then in that case your cx should be less than beta and beta should be less than alpha. Okay, so this is basically the condition that we assumed in the case of evanescent wave in the last lecture when we did the derivations of the evanescent wave, where transmitted wave was basically decaying with respect to depth, and for that purpose we considered that the apparent horizontal velocity should be less than the shear wave velocity, and its shear wave velocity will obviously be less than the p wave velocity. Now now come to the slide that we were talking about. So there will be three roots possible for this particular equation, and there will be only one root that will be satisfying this particular condition, and that root will be like this: cx is equal to 2 minus 2 by under root 3, that is will be multiplied to beta, and finally you will get 0.92 beta. That means horizontal apparent velocity of the Rayleigh wave will be slightly lesser than the shear wave velocity. Or you can say the apparent horizontal velocity will be 92% of the shear wave velocity, that is your beta. Now you know the value of the cx, then you can solve for the amplitude terms that are a and b. When you will do that, then you will get a relation b is equal to a in bracket 2 minus cx square by beta square by 2r beta. This should be your beta. It should not be rb, it should be your r beta. So when you will plug that into the displacement equation, that in terms of the potentials, then you can possibly solve for your displacements. So when you will solve for the displacement, that means your ux and uz, then you will get your displacement something like this. These are the harmonic waves, and you can see that these are depending upon these exponential terms in terms of the depth. So ux and uz both are basically decaying their amplitude with respect to depth. So now you can see when we draw those motions, those ux and uz on with respect to the depth, that will be divided by lambda, then you can see this is your retrograde motion, this is your retrograde motion, and this is your prograde motion. This is your prograde motion, and this is for your retrograde motion. And you can see that both of these motions are basically decaying with depth. That means the prominent motion will be happening near to the surface, or you can see the Rayleigh waves are trapped near to the surface. So here is what this looks like. The amplitude of the displacement diminishes with depth. The longer wavelength will have displacement at greater depth, since y on the figure is a function of the lambda. So if you have the longer period waves, then it will penetrate deeper into the depth, and it will be having more displacement at the greater depth, because there is this term that we are having, that is basically divided by the wavelength of the wave. So another way of putting this is that the sensitivity of the Rayleigh wave to the structure within the earth varies with the wavelength of the wave. So that these things that we have just shown you, this particular curve is also known as sensitivity kernels for the surface wave. Sensitivity kernels for the surface wave. Okay, so these sensitivity kernels basically tells you about how sensitive your Rayleigh waves are with respect to the depth. So Rayleigh wave, so what we have seen, the longer period waves are more sensitive to the greater depth. Now let's look at these figures. These are basically drawn to see how sensitive your Rayleigh waves are to the different physical parameters of the crust and the mantle. So three parameters that we consider are the density. This is your density, this is your p wave velocity, and this is the shear wave velocity. And there are the two color lines. One is for the 20-second period surface wave Rayleigh wave, and another one is the 133-second Rayleigh wave. And up to here we are showing the sensitivity up to the crust, and then after we are showing it for the mantle. So if you will look at it very closely, then you can see up to the crust, in the crustal part, the density, p wave velocity, and the shear wave velocity are all very sensitive for the shorter period waves. But as you go deeper, then you can see after the crust, the shear wave velocity is having much more sensitivity towards the higher period waves. So all in all, if you want to have these features to be looked into more closely, then what you can do, you can have your Rayleigh waves velocities computed at different points on the surface of the earth. Then you can in the form of group velocities or in the form of phase velocities. Then you can convert to the shear wave velocities. Now let's talk about the particle motions of the Rayleigh wave. If you remember, we saw these two equations here, this one and this one we just derived. If you want to look at the particle motion in x and z direction just at the surface, you can put in z is equal to 0 to see how the particle behaves near to the surface. So that is what we have done for this here. At z is equal to 0, that means near to the surface, we want to look at how the particle is moving in x and z direction both. So x direction motion will be having this sinusoidal kind of motion, and z direction motion will be having this kind of sinusoidal motion. So you can see that when sine this phase sine omega t minus kxx, this will become 0, then the cos term will dominate. That means the particle motion mostly or dominantly will be in the z direction, and this is what it is written, it is there. So at basically the omega t minus kx is basically 0, then the particle will be having this position here, that will be your in the positive z direction at an amount of about 0.62 akx. This is the amount. And then if you move on to having the value of t, that is equal to t by 4, capital T by 4, that means if you will take t as 2 pi, time period of the sinusoidal wave, 2 pi, then 2 pi by 4, that means it is around pi by 2, then this term will become maximum, and this will become the uz will become 0. So ux will become maximum, that is 0.42 akx. So this is your 0.42 akx here, this particular amount, this particle displacement here. And then likewise at t by 2, capital T by 2, the particle will be here. That is when your ux will be 0 and uz will be negative. That means because z is positive downward, so that means this is your negative here. So this means here it will be maximum in the absolute term, and then it will again be having the maximum value for the ux at 3t by 4 and minimum value for uz here. Likewise, so all in all, if you will see, the particle is going from there to here, and then here to there, and then coming back, and likewise it is happening. So this is your retrograde elliptical motion. So you can see what is written here, since cos and sine are 90-degree phase out of phase. So when we are drawing the particle motion of the vertical and the radial components, so you can see that these are the vertical and the radial components are drawn here in this particular figure. The dashed line is for the radial component and the solid line is for the vertical component. These are 90-degree out of phase, which means when one is maximum, another is minimum. When another is minimum, then the previous one is maximum. So that is what it is happening here. So since cos and sine are 90-degree out of phase, this means a particle on the surface is going through elliptical motion. Moving to greater depth, the sense of rotation changes from counterclockwise to clockwise. So that means near to the surface, the particle will be having the counterclockwise, that means opposite to the direction of the propagation of the wave, that means a retrograde elliptical motion. And if you are going to a deeper portion of the earth, the particle motion as the Rayleigh wave travels will be clockwise, and that means the prograde elliptical motion. That means the particle will be moving in the direction of the propagation of motion of the wave. So if we make a note of particle motion of the Rayleigh wave, then note that the exponential decay of the displacement is a function of the wave number, that is kx is equal to 2 pi by lambda. Thus, the degree of the exponential decay diminishes with the increasing wavelength. In other words, a longer wavelength Rayleigh wave will see deeper structure in the earth. Since in general the velocity increases with depth in the earth, this makes Rayleigh waves dispersive. This dispersion can be measured to infer the depth variation of velocity in the earth. So the summary of today's lecture goes like this. Surface waves are dominant type of wave in a typical seismogram. They can travel multiple times around the earth and cause much of the damage in the earth. At the larger distances, they can be more destructive. Since it has the lower frequency that can resonate to the taller buildings resonance frequency, then can make more damage to the buildings that are taller, that are at the larger distances. So the surface waves are useful in earth science because the different wavelength waves are sensitive to the different depth of the structure. Thus, if we can measure surface wave velocity as a function of wavelength, we can infer the structure of the earth. This makes a seismologist happy. Basically, I have told you the wave velocity of the surface waves are vary with the wavelength or the period of the frequency. As you can see, its variation with the wavelength or the frequency with depth, then you can basically make some comment about the structure of the subsurface of the earth. Some features of the Rayleigh waves goes like this. The Rayleigh waves have P and SV motion. We see them on the vertical and the radial channels of the seismogram. They need no special condition to exist, unlike love waves. They are not inherently dispersive. In the earth, they are dispersive because of the heterogeneity of the earth. So these are the references. And in the next lecture, we will talk about love waves. So thank you so much. Bye-bye.